In this video, I'm going to talk about the different ways that we can derive stiffness matrices for finite elements. And along the way, we're going to talk about the justification of finite elements using fundamental theories. This is the first of two videos that need to go together because of the depth of the topics. So in this one, I'm going to talk about the different options and then specifically focus on the principle of stationary potential energy. And then in the next video, we will use that principle to derive finite element analysis general equations that we can use for each element type. There are four different methods to find the FE form of the boundary value problem, and all of these are used to varying degrees for different element types in stress analysis. The four types are equilibrium, direct stiffness, variational, and weighted residual methods. So equilibrium we've seen already. We previously used this for the bar element. However, because it requires being able to cut elements in parts and look at force equilibrium, it's really only useful for simple elements. Direct stiffness is kind of similar. It uses virtual displacements and physical reasoning to determine reaction forces. Therefore, it's really, again, only useful for more simple elements. Variational methods are more robust, more useful for different types of elements. However, the full derivation to show that this works requires an understanding of variational calculus. We're going to skirt beyond that a little bit in this class, but this is the method that we're going to use to develop the more complicated elements. And finally, the weighted residual methods. These methods are probably the most robust in the sense that you can use them on any type of boundary value problem. However, they're somewhat less satisfying than other methods that are out there. They don't provide a whole lot of insight. So they're important methods to know, but we're not going to be using them in this video series. In order to use the variational approach to develop a finite element formulation for a problem, you need to have some form of a functional. A functional is a function that depends on other functions, and it has certain characteristics in the system that you're analyzing, in this case, solid mechanics system. Now, it just so happens that energy methods provide the functional that's necessary to derive the finite element formulation for stress analysis. And the functional is total potential energy. There's a principle in solid mechanics called the principle of stationary potential energy that states, among all admissible displacements that a body can have, the equilibrium displacement is the one that minimizes or makes stationary the total potential energy of the body. Now here, admissible displacements are those displacements that actually can work in the physical part. In other words, they satisfy boundary conditions and they satisfy material continuity or compatibility. Let's take a look at that total potential energy functional and apply that to finding the equilibrium position for a spring. Now, most of you are familiar with the spring application. You have a spring, a tension spring in this case, that sits at a certain distance, and then you add a weight to it and it reaches a new equilibrium length. And a common problem in spring analysis is to find that new equilibrium length. Well, this is finding an equilibrium displacement for a system. So in this case, we want to use the spring potential energy in order to find that equilibrium position rather than doing balance of forces, the more typical approach. The total potential energy for any problem, not just a spring, but for any problem, is defined to be the sum of two factors. The internal energy stored within the system, we just designate that as U, and the potential of the forces external to the system to do work on the system. So that's omega. For a spring, the internal energy is often written as 1/2 kx squared, where k is the spring constant. That can be easily drawn, as shown here, where we have the u function identified in green, and it's a parabola. The omega for the spring case here, the external force that has the potential to cause or to do work, is gravity. So the force is mg, and the work that it would perform with a positive x is mgx. So the potential that it has to do work is the negative of the work that would be performed. So omega is equal to negative mgx. If we add that, you see that's a straight blue line in the curve, in the graph. So If we add these two together, we can get the total potential energy in the system, consisting of two pieces, the internal energy of the spring and the potential of the forces to do work. So that's the final yellow curve there. Pi p is 1/2 kx squared minus mgx. So now that's the total potential energy. We want to find the minimum potential energy location that should be the equilibrium displacement. So when does min pi p occur in terms of x? To find the minimum potential energy, we take the derivative of the potential energy function with respect to position. So d pi p dx is equal to 0. Evaluating the pi p function, taking the derivative of it with respect to x, we get kx0 minus mg is equal to 0. Now x0 here represents the new equilibrium position. So x0 is mg over k, and this is the exact same result you would obtain if you did a force balance or equilibrium analysis of this problem. So this is just a quick demo to show you that looking at a spring case that you're familiar with, we can apply this principle of stationary potential energy to get the same result. Before I get into any calculations, I want to talk quickly about how this principle of stationary potential energy gets used in deriving finite element analysis. So the principle can be restated as, of all the possible deformations of a body, the equilibrium deformation has the minimum total potential energy. In other words, min pi p, that's what we're looking for. I could restate that again as the total potential energy of a system is stationary or minimum when the system is in equilibrium. Or another statement of that using variational calculus is that the variation of total potential energy at equilibrium is 0. So again, we'd need to fully understand variational calculus in order to be able to use that expression, but we can get close to that using differential calculus and a little bit of hand waving. So that's what we're going to do through the rest of this video. Actually, just one slide worth is where I'm going to do my hand waving. Otherwise, you'll see it flows very nicely from the calculus of differentials that we're more familiar with. In order to derive FEA using stationary potential energy, we need to start out with the realization that the total potential energy always depends on the deformation of the system. If it's internal stored energy, then there's local strain, and that's local deformation. If there's work being done to the system, then that is overall motion of the system, or again, deformation of parts of the system. So we can write the function, the total potential energy as a function of the degrees of freedom of the system, all of the nodal displacements. Then given that this depends on each of those variables, we can use the chain rule to find what the variation of pi p is equal to. So the total variation, d pi p, is similar to total differential, and we use the chain rule of all of the variables that pi p depends on. So d pi p is equal to derivative of pi p with respect to d1 times the variation of d1, and so on, adding each one of those nodal displacements in. Now the sum of those has to equal 0 if we are at equilibrium. But because each of those variations are independent of each other, they can't be all 0, and they can't be related to each other in such a way as to become 0. They are independent. So we need to say that each of the coefficients of the variations must independently go to 0. All of them must be 0. So in other words, the derivative of pi p with respect to every degree of freedom must be 0 in order for the variation of pi p to be 0. The neat thing here is this now forms a system of n equations, one for each of our nodal displacements. Notice that we are looking for nodal displacements to solve the problem. So we have n unknowns, the d's, and we have n equations. So this is looking pretty good. This looks like a system of equations that we might be able to use. We write this expression, the derivative of pi p with respect to each one of the nodal displacements, in short form informally as d pi p d vector displacement. This is not a defined mathematical term. You can't take a derivative with respect to a vector. But what we mean by this is the system of equations that is formed when you successively take the derivative of pi p with respect to each term in the vector d.